right, how's it going, everybody? We're going to go ahead and take a look at section 1.2 today from our textbook. We're going to talk a little bit about data types, graphical displays, sampling methods, and a tiny bit about variability. The book is doing a nice job of never leaving variability out of the discussion, but they haven't quite gotten around to defining any of the specifics that we need to look out for with variability. So we discussed it a little bit last video. We're going to talk about it a little bit more again this video, but I kind of think that the book is just kind of trying to make sure that you don't forget that this is an important part, even though there's still kind of no details about the variability yet. I'm just trying to keep some other information up here above my head. I think I'm just going to always say when the next lecture is up there and stuff. So this is our second out of two this week. So the next lecture will be part of week 2. It'll be on, so our next lectures will be on Monday and Tuesday of next week. We'll look at sections 1.3 and 1.4. And then I believe we move into chapter 2 for the Tuesday lecture. So let's talk a little bit about data types and classifying data here. So in the text, you've read through a bunch of these definitions. There's a whole mess of words in bold. Certainly the number of definitions per page will go down as the semester moves along here. But there's, on the classifying data page in our textbook, a significant amount of vocab words stated there. So I think that a helpful thing is to see a diagram of how these all relate to each other rather than just listing all of their definitions. I think it's good to kind of have a visual sense of the relationship between each of the data types. So I went to, rather than make my own, I know that there's probably a billion out there on the internet already. So I went to go search for one, and I actually found a little bit more variation than I was expecting to find in the types of display representations that I was seeing. I guess people are classifying data very slightly differently, and so I think that's a good thing. I want to show you what I was expecting to see, and then I want to show you some other interesting things that I saw that I think are worth mentioning. So what was I expecting to see? I was expecting to see this exact diagram right here. This is stating to us any of the variables that we are interested in discussing this semester can be broken down as qualitative or quantitative. Some other words that we might want to use here. That quantitative, actually, let me maybe just write on this document right here. When I'm seeing this quantitative, what I'm thinking to myself is this should be our numerical data. And by the way, this is one of those things where I remember spending years being like, I can never remember which one's which, quantitative, qualitative. They both are obviously very similar sounding words. I basically just remember that their back half is the same. It's the tative part is what's not helpful to me. I will remember quantity is about amounts and quality is about features. And so when I see these two words, I see quality and I see quantity. And so these are also given as categorical and numerical. These are just kind of alternate words for qualitative and quantitative here. So those are the same, and those are the same right there. Each of these then breaks down a little bit further, right? So we're talking qualitative variables. We're talking about things that break down into categories. Then we have some more prefixes here that we want to keep track of. Nominal, nom, is our Latin root for name. So this is just the name of a category. So if I were talking about student ethnicities, then we would be talking about Caucasian, Latin American, African American as names of ethnicities. Those would all be data types that we could have associated with each of us individually. And in this way, there's no numerical relationship. There's no distance between them. They're just names of categories to which we belong. Other things are ordinals, things that give order to something. If we're talking about places that somebody came in a race, then we've got first, second, and third. Those are still categorical. I still can't measure a difference between first, second, and third, but I do know that first comes before second and second comes before third. So there is a natural ordering to those. And again, if we come back to our ethnicity example and nominal, there is no natural ordering to ethnicity. There is no order that you would put ethnicities in one that makes more sense than any other. But if we're talking about completers in a race, then it makes sense to list them according to their completion. So there is an ordering, and that's how you can remember what ordinal is doing, is there should be some ordering that's associated with these guys. So these have a ordering even though they're not numerical or measurably numerical. We'll talk a little bit. I've got a good example in a second that's going to help us identify how to distinguish between the numerical and the non-numerical for things like the place that we came in a race. Our other branch of variable types here is the quantitative or the numerical data types. These in general, as a mathematician, I prefer to work with these. Quantitative data, we're going to see a bit more of this semester, partially because it's easier to do data analysis with. The distinctions that we want to make with our quantitative data is data points that are discrete versus continuous. I think discrete is a word that some people generally don't like, but continuous is usually good. And since you just have to distinguish between the two, hopefully it's more of a process of elimination that helps you figure out what you're looking at here. When I'm thinking of continuous data, I'm thinking of data that can take on any single value in an interval. Right? So when I think about the age of a tree, that should be a continuous variable because any tree's age, it's not like we have to just automatically jump from one number to the next number. We could be measuring this in years, months, weeks, days, minutes, seconds, tenths of seconds. We could break this down as finely as we choose to make that classification. Or excuse me, to make that measurement. The alternative here is discrete data. Discrete means that you have only a certain number of choices, although they are numerical and they are measurable between them. My classic example for discrete data is something like the number of children that a family has. There's no way to have fractional amounts. There's no way to have negative amounts. And we also know that there's an upper bound on this, right? Like even with our quantitative data, we don't want to be saying like it can take on any value. I think the most known, and here's oh man, every time I say this fact, I think a bunch of people don't care and like 5 people have their minds blown. Right now, the record for the most known children by a single person, I think is something like 64 or 65 children by a woman. It was across like 16 or 17 births, and like most of the births, she had like a couple sets of quadruplets, some twins, some stuff like that. Anyway, so there's an upper bound on the number. That's all I was trying to get at right there. If we're talking about number of children in a family, it seems like 0 through 65, whole numbers only, are the only options, right? So it's discrete because it's measurable. We could do math with those numbers, but you could never pick fractional values, negative values, and obviously there's going to eventually be an upper bound on how many children you can have there. So this is really, I think, our good breakdown here to realize that we are first making a distinction. Is this numerical data or is this categorical data? Quantitative, qualitative, just alternate word choices there. Once we've made this distinction, then we decide if it is categorical or qualitative data on the left here. Are we just looking at names of classifications or is there some natural ordering to those things? If we're looking at numerical data, we want to ask, could that variable take on any value? That would be continuous. Or is it essentially only whole number values? And by the way, it doesn't just have to be integers. Maybe we're in a situation where we count things by fives or whatever. Maybe your options are 5, 10, 15, 20, 25, 30, for example. That would still be an example of discrete quantitative data right there because there is a finite number of choices that you have to choose from, but we can measure exactly the distance between each of the choices. So again, this is the diagram I was expecting to see. This to me is what's representing the ideas that we're seeing in our book. So I did see some other things though. I like this one because I do a bunch of programming and I thought this was a little bit interesting of a way that a programmer thinks about data very slightly differently. And by the way, what the website that I found this at is Machine Learning Mastery. And what machine learning is essentially programming for what modern movies would like to refer to as AI. And really all AI is, or machine learning is, it's the perfect union of being a computer programmer and a statistician. It's helping teach a computer how to make the smartest possible predictions based on the data that it has available. So machine learning is actually kind of one of my personal interest places here, and it's because I do like math, but I really like programming and statistics quite a bit, and that comes together in machine learning. And so I think that this is a very appropriate alternate view of our data types right here. You can see that they still break them down into numerical and categorical, what we had previously called, remember, numerical is quantitative because we're talking quantities. Categorical is qualitative because we're talking about qualities. And they describe their further breakdowns of these a little bit different and give some nice examples. Notice that in our previous diagram, numeric was broken down into continuous and discrete. But the thing that you should think about, regardless of how much you know about computer programs, is that we can't necessarily think of like literally every single number that could ever be in a computer. A computer is going to have to do like decimal place values and stuff, essentially giving us decimal approximations for things. So rather than break these down into discrete and continuous, they break these down into into integer, and float is a computer word. A float is just any number that requires a decimal point to be expressed. Computers just make this distinction because these take a little bit more data to hold that value versus integers that don't require any decimal point to be expressed. We can hold in a computer, we can tell what an integer is with slightly less data. So this is held a little bit different way in the computer than decimal point values are held. So this integer versus float distinction. But this is just a programmer's way of saying integers is like discrete because we're only going to pick whole numbers. Float is like decimal point values, so we can make a very, very fine measurement versus having to jump all the way from 1 to 2. There might be lots of values in between 1 and 2 that we could select. In the float case, we're considering them all to be like decimal values here. But again, just kind of given different names. Integer and float are the programmer's version of discrete and continuous right there. In the categorical branch over here, we do have some more examples over here. Nominal, their example is RGB for red, green, blue. Colors are a good example of nominal data. There is no natural ordering to colors. There's no color that comes before other colors. Ordinal data, exactly as I said, they've got some first, second, third rankings, I think, are a good thing for ordinal data because there is a natural ordering. But like if we're talking about, who came in first, second, and third at the at the cow showing event at the 4-H fair, just because one person placed above another person, I don't have a way to meaningfully measure the distance between person that placed first and the person that placed second. We lose our ability to measure, even though we're still in a sense talking something that's vaguely numerical, right? First, second, third, those are numbers, but they're not things that you can measure the distance between. And so that's why those don't qualify as anything numerical. Finally, they have a third category of categorical things that's very appropriate for computer programming type things, but I really think is appropriate for us to kind of think about in other contexts. A Boolean value named after George, I think it's George Boole, Boole. It's a very famous guy from the 30s, 40s, 50s. Kind of was one of those people. It's like the father of computer programming. He's one of like those the big like 5 or 10 kind of like early academics that kind of invented the sort of theoretic structure of what computers were going to be like before we had computers. So, real important guy, and he got a category of things named after him. A Boolean value is a value that's true or false. Those are the only two things that you get. And things that are true and false just come up so often in computer programming and in a lot of statistics stuff out there. So I do think it's pretty appropriate that they gave it its own category. Otherwise, I would probably just lump Boolean into the nominal category right there, since it is just a classification that doesn't necessarily have an ordering. But I do think that's not an not an unusual thing to do, even though I've never seen this in a table like this before, a diagram like this before. Makes a bunch of sense to me, especially why a programmer would think of that. So this is just like an alternate version of the same things that we're thinking about. A little bit different names, a little bit different context, same concept going on here. There's one other alternate breakdown that I found, and the reason I wanted to include this one, even though I like it slightly less, I want to talk about what's different about it, why I like it less, and where you're going to see it. What you should notice about this third and final one right here is we're still talking all data types. We're still going to break them down into categorical and numerical. And again, categorical and qualitative are the same. These are qualities. Numerical and quantitative are the same. These are quantities. They still break down categorical into nominal and ordinal, same exact thing as the previous two diagrams have done. In this one, though, they break down numerical differently. They refer to these as interval and ratio categories here. The reason I wanted to bring this up is because I understand very broadly the value in making this distinction, which I'm going to kind of describe in a second here. But what I am thinking is that this distinction isn't going to be as practical for us to make this semester as the nominal and ordinal, or excuse me, as the continuous and discrete distinction is going to be. Continuous discrete is going to help us identify what type of scenario that we're in to tell us, for example, what type of probability distribution do we want to be using to help make a certain type of computation. Interval and ratio, I think, is getting a little bit more towards some, I don't want to say like more like advanced topics in math, but what they're describing with interval and ratio is that some numerical systems um, do are okay with doing, for example, addition and subtraction to make measurements between two amounts, but aren't okay with doing division between two values to make representations of amounts. Our book makes this distinction in section 1.3, by the way. So in a sense, this interval and ratio breakdown is me getting a smidge ahead of myself. It's section 1.3 stuff. But when they talk about interval and ratio, they say that things like temperature, for example, it makes sense for us to talk about the difference between 60 degrees and 80 degrees is 20 degrees. And the difference between 20 degrees and 40 degrees is also 20 degrees. And so it makes sense for us to do, for example, subtraction to measure difference between amounts when we're talking temperature. However, because all of our different temperature scales use the number zero differently, it doesn't really make sense for us to necessarily do division of values. For example, things like 80 degrees is not really necessarily four times as hot as 20 degrees. And part of the reason is because I didn't even just tell you if I'm measuring in Fahrenheit or Celsius. In Celsius, at least 80 degrees is four times away, four times further from the freezing point than 20 degrees is. But that's not true in Fahrenheit. In fact, in Fahrenheit, 20 is below freezing. It should almost be considered sort of like a negative type value. And if we're thinking about freezing being our good center of reference, in any event, the whole point is this interval versus ratio distinction is saying, does it make sense to do subtraction and addition between those numbers? If so, then we at least qualify as interval. If it also makes sense to do multiplication and division between your variable values, then we also qualify as being a ratio variable there. So again, I'm going to say you're going to see these words as definitions in 1.3. I am less interested in your ability to classify between interval and ratio, and I am more interested in your ability to classify between continuous and discrete as our breakdown for numerical. So I'm glad that I saw this chart in here, and I'm glad that it made me remember that I saw the interval ratio stuff out there in 1.3. And I'm just going to say, again, I'm more interested in continuous and discrete as our understood breakdowns of numerical rather than interval and ratio. I just think it's going to be more helpful to us for our purposes this semester here. So let's walk through some examples here. I know there's a whole mess of examples in the book. I know this isn't too crazy. A couple of these, I feel obligated to do this. There's a couple in here that are a little bit special that I want to kind of point out a special thing here for you. So let's kind of just walk through these guys here and let's see if we can identify the type of data. So first one here, we got distance to a grocery store. As soon as I see distance, I am thinking that we're measuring something numeric. And when I see that we're measuring something numeric, then I want to ask myself, is this something that we are measuring finely? When I say finely, I mean, is there like small units of measurement that we could use here? Or is this something where we need to chunk this up into larger groupings of numbers, like 1 mile or 2 miles or 3 miles? I think that I live close enough to the grocery store that it makes sense for me to be measuring this not just in whole miles. I'm like 2.5 miles from Winco, right? I'm like 1.5 miles from Safeway. So in this case right here, distance I'm trying to think of a counterexample. In almost every case, distance should be numerical. And I think in this case here that we should be, let's see, numerical. And I think that this guy right here should be continuous. And I think it's continuous because I think I could give basically like any distance at all and it would make sense, right? I don't need to pick a whole number value. The number of visits to the grocery store per month, again, keyword right away is it says number, so I'm hoping you're thinking that this is numeric, but I can't really take a half trip to a grocery store, right? So in this case, it only makes sense for me to talk about whole number trips to a grocery store. So in this case, I think that we are looking at numerical, but I think discrete in this case. So I'm going to start using abbreviations for all these guys, numerical, discrete. Number 3, a list of the top 3 grocery stores in Eureka. When I say top 3, that's indicating to me that a ranking has been performed. And so in this case right here, our things that we're listing are the grocery stores themselves. So our variable value is the grocery store. One value that the variable might take on is Winco. And that might have a ranking relative to the other grocery stores. Everybody knows that Winco is like the best grocery store it's ever happened, clearly at the top of the list. So it looks to me like since the objects that we are, the data that we're collecting is the name of a store, that should be categorical or qualitative. And it looks like in this case, we're talking about an ordering of some of those things. So this should be ordinal because it is a ranking. A ranking of the top 3 runners in a race. Now I'm starting to bring in some of these ones. Number 4, number 5, and number 7, I guess, are intended to be a little bit less obvious right here. And so the 3 runners, so again, this is going to be categorical. I want to emphasize it. Okay, all right, sorry. Let me back up real quick. Since the variables in this case are who is the person that came in first, who is the person that came in second, who is the person that came in third, this is going to be categorical because what we're doing is we're collecting people's names once again. Again, we're ordering these. And so this is going to be ordinal again. But I want to draw like a little distinction between 3 and 4 that I can't otherwise draw with our current categories here. The difference to me is that if I'm looking at the number 1 ranked grocery store and the number 2 ranked grocery store in Eureka, there's no way for me to come up with a measurement as to how much better was the first store than the second. And even if we all like rank this out of like 10 stars or something like that, there'd be a star difference, but like, I don't know, that's a pretty weak. It's weird for me to be like, no, that grocery store is 1.2 stars better than that grocery store. I don't really know what that means, right? That's a bit of a vague measurement right there, if anything at all. On the other hand, if we're talking about a ranking of 3 runners in a race, this is something where we do actually have a little bit more measurement capability. So we are talking categorical because the variable is who is the person that came in that ranking. It is ordinal because we've ranked them in order. There is a natural ordering to that. We put first place first and second place second. But the thing that makes 4 a little different than 3 is I have like an objective measurement of exactly how much better first place was than second place because I could just subtract their race times. And I know that first place has a shorter race time than second place based on the ranking. So notice in this case here, we even have like a little bit better than ordinal in the fact that we can actually objectively measure what those race times are and how much more first was than second. But again, since our data were the runners themselves and not the race times, this is categorical. If I was talking about the top 3 race times, then that is something that we would probably consider to be numerical and continuous. But since we're talking about the racers themselves, that is categorical ordinal, but we have a little additional measurement capabilities because time is something that's easy to measure versus goodness of grocery store is something that's hard to measure. Okay, so there's my little special thing. Maybe I should just put a star next to 4. Like this had a little something different going on, right? Number 5, a large meat producer labels each package with the number 1 through 6, indicating which of its 6 meat packing plants it came from. This is just a thing that pretty much everybody does. This is just a quality assurance thing. They need to know if there's been a mistake, how to trace it back to where it came from. I'm actually pretty sure the FDA probably mandates this kind of stuff for food safety things. So this is a pretty typical type of thing to do. So the reason why number 5 as an example made it onto my list here is because number 5 is intended to be sort of deceiving right here. I literally the word number is in here describing this thing. I'm putting a number 1 through 6 on this package of meat, right? I'm just picturing a pound of ground beef. It's got to have a label on it as to what meat packing facility it came from, and that's just going to be a number 1 through 6. My question to you is this really numerical data? And here's my question for you. If I were to, for example, ask the question, how many children are in your family? I think that's also a question where almost every person I talk to is going to give me an answer of 1 through 6. Or how many, how many children, I guess if you have 1 through 6 people right there. I was just trying to think of 0, but if I'm asking you, you are the child in your family. So it would be like, how many children are there, you plus your siblings? The answer is at least 1 because you exist. And a vast majority of family sizes are smaller than 7 children out there. So the distinction I want to make is this. If I were to ask the question, how many children are in your family? You're all probably going to tell me 1 through 6. Maybe some of you lucky people are in a huge family out there, a little bit bigger. But the point is, I could then do things like say, I have collected data from 40 statistics students, and I found that their average number of children in their family is 2.4 children per family. That's a sensible thing. And even though I know that there's no such thing as a family having 2.4 children, I can interpret that average as saying the average family has between 2 and 3 children, right? And even though I just said the word between, none of us are thinking that I'm talking about a fractional child. We're just all understanding that there is variability. You might have 2, you might have 3. That's about average right there. If 2.4 is average, we expect slightly more families to have 2 than to have 3. Stuff like that. Bring it back to our meat packing now. Does it make sense for me to grab 15 packages of meat and look at all of their meat packing plant numbers and average them and say, the average package of meat came from plant 2.4? that makes way less sense than averaging the number of children that are in your family, right? So in this case here, what you should kind of notice is that even though these meatpacking plants are labeled by number, they didn't have to. They could have called them words. They could have called them meat packing plant alpha, beta, gamma, delta, epsilon, and zeta, or something like that. Giving them Greek letter names. Who cares? Any naming system would have worked other than numbers just as well for them. And so here, this is a bit of a misleading one. It seems like numbers were used as categorical identifiers. We're trying to just label a meat packing plant. It's basically just a coincidence that a number was what was actually used. And my big argument for this one, why you should be able to identify this, is because it does not make sense to do things like compute an average meat packing plant. Right? It does make sense to compute an average number of children in a family. So one of the things I'd encourage you to think about is that when you're deciding between categorical and numerical, it's not numerical just anytime there's a number involved. It has to be numbers that you would do math with. And in this case, I would never do math with this meatpacking plant number. I wouldn't ever compute an average of it, for example, and therefore it doesn't qualify as a numerical piece of data because I don't do number type stuff with it. I'm going to do category type stuff, like say, for example, what proportion of them came from meatpack plant number 2. That's something I would do because it's a category of plant from which they came. So number 5 is our a big misleading one. It even literally says the word number, but we're not looking to classify this as a numerical. This is going to be categorical. Now, whether this is ordinal or not, I actually honestly probably need a little bit more information. I would have to assume any reasonable company is going to order their meatpacking plants in order. I would have a hard time believing that they would open up their first plant and call it plant number 4 and then make another plant and call it plant number 7. So I'm kind of assuming that if this is a reasonable company, then plant 1 was probably their original facility and they expanded into plants 2, 3, 4, 5, and 6. But I don't technically know that. So I'm thinking that this is ordinal, as in plant 1 came first time-wise. But in this case right here, I don't know. I might not even care to ask you whether you think that this is ordinal or nominal here for these names. And so I'm just going to write both because that's not the thing that I'm worried about in this one right here. The thing that I'm worried about is that we can distinguish between the categorical and the numerical. So the second breakdown there is not really the interesting thing to me. The interesting thing to me is that sometimes we classify numbers as categorical variables because sometimes there are numbers out there that you would never do math with. So remember our numerical categorical distinction is not is it a number or not. It's is it a number you would do math with or not. That's really our numerical categorical breakdown. Number 6, student ethnicity. This is one that we talked about a minute ago. I brought up this one specifically because the book uses this pretty heavily for a lot of its examples right here. So we want to remember that an ethnicity is obviously never going to be a number. So this should certainly be categorical. And there's never going to be an ordering to these things. So this is just nominal. And remember that the Latin root nom means name. It's just the name of the ethnicity. That's all we're doing right there. So identifying proportions of students that belong to different ethnic groups, something like that. We can come up with, are you a member of that group, yes or no? Because these are categories of groups. Finally, number 7. Number 7 is another one of these things that's almost like saying you could tell me an answer to this and your answer might be different from mine. As long as you can justify it, I'm good with that. Because I think that this one could go a couple different ways. So time required to run a race, or time to run a race. I don't even know why I have required in there. Time to run a race. So here's what I'm thinking. One, hopefully we're all down with the fact that this should certainly be nominal. Or excuse me, when I'm saying nominal, I'm thinking numerical. Numerical, we're looking at times. So I do think we're looking at a numerical. What I want to ask is what argument could you make for this being discrete, and what argument could you make for this being continuous? And here's the way that I like to think about this. In general, I think it's really good to think of time as always being a continuous variable. Time should be one of those things that no matter how much we've broken it down, there's always further subdivisions that we could go. If we wanted to measure a person's time to run a race down to we could measure to 20 decimal places of accuracy of time if we got out things that measured individual atoms distances away from each other and stuff like that. If we wanted to spend $1 billion, we could probably get insanely accurate readings of the time that we're going to run a race, right? So in that sense, I think it's good for us to think of this as a continuous variable. However, what really happens when you run a race, right? And so I'm picturing like you're the guy running the 100-meter dash, right? And I mean, even at the Olympics, like how accurate do they really measure this stuff down to, right? And what I can really tell you is if you're like Usain Bolt, if you're like the fastest dude on earth, you really don't care about hours and you don't care about minutes and you really don't care about seconds because he's such a competitive runner. But I don't know, look up Usain Bolt. He's the world record holder for, he might have both the 50 and the 100 meter. I think he at least had both at some point in time. Whatever. The point is, super crazy fast guy. Um, anybody, there's no such thing as a person being a full second faster than him in either of those races, and those races are so tight that I can't imagine the last time that he ran against anybody that he beat by a whole second either, right? So like in his mind, he lives on the scales of tenths and hundredths of seconds. I think that a thing to think about here is that when we are talking about how we measure time, ultimately, whatever time measuring device that you're using has a finite number of decimal places, right? Like it's only going to have two or maybe three decimal places. So it could be the case that you could think of this as a bit of discrete as long as we're like really, because we're really focusing in on like a super narrow window of times, right? Again, if you're using bullet, what is it, like a 9.63 seconds or something like that was his like 100 time. I'm sure I'm getting all these numbers wrong right now. But anyway, like 9.63 versus a 9.64 is a huge difference to him, right? And now it might not be to us, but to all the people that are competing for the world record, it is. So in that sense, right there, it might be that we think about this being more discretized, discrete, because in this case, we do just sort of make a jump from the 9.63 to the 9.64. Technically, there are some times that are in between there, but they're very, very small times. They're very finely measured. And on the stopwatch that they're using, they wouldn't be able to make that distinction between them. So in some special cases, I do think it makes some amount of sense to measure time as a discrete numerical variable. Um, I think it makes more sense to always think of time as a continuous variable. But if you were to make an argument for me as to why you wouldn't think of it that way in a certain context, I think I would always be open to that type of argument. And in a broader sense, I also feel like I should say, like in this class, like there's sometimes going to be times where you're like, I don't feel like that's the appropriate way to think about that. Here's how I think about that. Make arguments for these things. This isn't a class about being right or wrong. This is a class about doing some critical thinking and making an argument. So if you feel strongly about something, then defend yourself and know that you're right. Defend it. So I'm for that. So I'm technically writing continuous here, but if I could see a person making an argument for discrete and me accepting it in this case right here, certainly as long as you justified your answer there. So again, time can get a little weird. Time, in one sense, kind of always continuous, but we always have a limit to the fineness to which we measure time, and so it always kind of has a limit there, which could cause us to think of it as being something discrete. So I think that's all we got for data types there. We talked about that for solid 30 minutes right here. But data types are really important. They're going to inform us of what we should be doing with all of our analysis all semester. So it's going to regularly be a thing where we say, what type of data is that? Oh, okay, so I should be doing, process A, B, or C right here based on our answer. So coming back to these data types matters. Graphical displays. There's a couple graphical displays we're going to use a lot this semester. There's a couple that we're not going to see very often. So let me kind of give you the highlights and the lowlights here. I'm going to spend a little bit less time on this. One of the reasons that we need to know what classification a data type falls into is that we know what type of data analysis to perform. We're not going to be able to do certain types of data analysis on categorical data because we can't make computations between ethnicities. Whereas if we were talking about all of our ages, there are computations that we can make, and that's going to allow us to do different types of analysis. So the analysis that we do in any given context depends on what data type we're looking at. The other reason why we need to be able to distinguish between different data types is that we need to know what type of graph we should use to visualize data. So the book lists some here. There's not really too many, and I think that most of us have seen most of them, like at some point in our life, somewhere on the internet, in a newspaper, stuff like that. So I just kind of want to talk through the things that students typically do wrong with these, because these are, I don't know, I think these are pretty basic graphical displays here. I don't think anybody's mind is getting blown when they see any of these graphs right here. So let's kind of briefly go through these. If we're talking about categorical data, we're often talking about what a common thing to do is to say what proportion of people in the population fall into each of the given categories. In that case, we might be talking about 100% of the people in the population, in which case a pie chart is a good way to represent proportions of people. I'm going to show you a bunch of terrible. Okay, I'm just going to say I basically don't like pie charts. It's really rare in which it's the best thing to do, and so I'm mostly going to show you terrible examples of pie charts here rather than any good ones. A bar chart will also do the same job as a pie chart, but it has a lot more flexibility. The risk with bar charts is that students often confuse bar charts with histograms, and so we want to make sure that we have a distinction between those two. As you can see, we don't use them for the same purposes, so we want to make sure that distinction is there. A Pareto chart, you basically don't have to worry about that. A Pareto chart just says sort your bar chart from highest to lowest. So a Pareto chart is a bar chart. It's just a sorted bar chart. So I almost don't like that the book even makes that its own whole vocab word right there. The Pareto just means sort the bars from highest to lowest on your bar chart. So let's kind of look at some examples of these. I'm going to come back up here and talk about, well, actually, I'm going to draw an example of a bar chart in a second right here. So let's talk categorical ones first, and then I'll come back and talk quantitative. So first thing that I want to say is the important thing that people need to be aware of is that pie charts out of all of these graphs have one restriction. They have one kind of like requirement where you can't use it unless you meet one condition. I hope that you read about that in the book. The whole purpose of using a pie chart is that we think of this as being one whole circle. And therefore, if you don't represent 100% of your data in your graph, then the pie chart doesn't make any sense because you don't have a whole pie that you're describing. So must have 100% of data represented. That's not the case in other charts. In other charts, we can, in a sense, just leave off other information. We probably want to indicate that it's not there, but the pie charts literally just don't make sense if you don't have all 100% of your groups represented. So I'm going to show you some bad pie charts right now. All these are bad. Some of these are technically okay, but they're all bad. So this first bar or pie chart, I don't literally even know what it's trying to tell me here on the left. Are Newt Gingrich, Sarah Palin, Mitt Romney, Mike Huckabee. This, I don't know, maybe this is like some favorability poll or something like this. This doesn't make any sense. These numbers don't add up to 100%. I'm looking at one whole what. Like this is a really bad way to represent this data because what none of these percentages represent is a proportion of something relative to each other. These do represent proportions of maybe I'm anticipating this is like proportion of registered Republicans who would vote for that candidate if they were the nominee or something like that, right? So these percentages do represent a proportion, but it's not a proportion relative to the other groups, right? It's not like 70% would vote for Sarah Palin over Mike Huckabee or something like that, right? So again, pie charts have to add up to 100%. If you have less than 100% or more than 100%, that was a completely improper use of a pie chart. Even if this was some comparative thing right here, I still probably wouldn't put this in a pie chart. Here's a pie chart over here that upsets me because the whole reason that this pie chart was created was for some statistics snob to be able, technically, this is a correct pie chart right here. Yeah, sure, maybe it's correct. The reason why this is technically a correct pie chart is because this does represent all Americans. So in a sense, 100% of all data was included here because this is representing 100% of all Americans and the way that they voted in the 2016 general election. We've got votes for Clinton, votes for Trump, and people that did not vote, and people that voted for somebody else, right? So this represents 100% of all registered voters, I'm assuming, but from government data right here. So technically, this is a good chart right here. But again, when I think of pie charts, I think of one whole object as representing 100%. And so I really don't like pie charts that use actual numbers rather than using percentages. What I'm always trying to get a sense of in a pie chart is what share of the pie is each category looking at. I always want to see a proportion, a percentage. And this is maybe just a personal thing for me. Like I agree with whatever person made this pie chart here that technically this is a valid use of a pie chart. It doesn't mean it's good. And our goal this semester, whenever we're graphing things, is to actually help ourselves out. And so again, this may be more of a personal thing for me, but I feel like pie charts should always be percentages rather than whole values right there. Now, here's another one. where these two are partners. These two graphs right here, these kind of go together. This is the real illegal one down here on the bottom left. This is where what we're trying to do is talk about. So, and by the way, let me make a distinction. Both of the graphs on the left don't add to 100%, but they're both bad for different reasons. This one's bad because the percentages are not comparable to one another. This wasn't 63% of Mike Huckabee relative to Mitt Romney, right? Down here, these are. This is saying out of all the Google tutorial searches, what programming language did people search for the most often? So this 10.4% is out of a 100% that the 2.6% is also out of. Like these are now out of the same collective 100%. But the problem with this pie chart is it doesn't represent 100% again, right? So the big thing that's important for pie charts is if you're not going to include all 100% of your data like actively described, then there has to be a category for other that contains everything else. Whether you describe it or not is, I guess, up to how friendly of a person you want to be in graphing your data and helping other people understand it. But there has to be an other category to kind of fill in the blanks because pie charts have to get to 100%. So other will get you the rest of the way there. I'm still going to say that I think that this is a really bad pie chart. And the reason I think this is a bad pie chart is because anytime other represents more than 50%, then I probably want to know what all the other stuff is. Like it seems to me like, it looks like about 70, almost 80% of this just didn't even get represented. Yeah, actually exactly 80%, right? This is exactly 20% right here if we have these numbers. So this is 20%, 80% falling under other is a little stupid to me. Like this I want to know what's in the other category, I guess. So all of these are things that I think are, in a sense, misuses of pie charts. I feel like people like pie charts because, I don't know, Excel makes them for you or something like that. That's not a really good justification for me to appreciate a pie chart. So let's kind of go back now and say you should be pretty confident that you should be using a pie chart, or else you should probably be instead using a bar chart. Well, I just want to, real quick while I'm on the screen, I just want to remind us, a Pareto chart is just a bar chart that's organized according to heights in order. So it's just a sorted bar chart. So nothing big to talk about for Pareto chart. What I want to talk about now is the distinction between bar chart and histogram. And then I'll come back and say a couple quick things about line graphs. We won't see those till later in the semester here. Bar chart and histogram is next. So what jobs do bar charts and histograms do? They both do the job of measuring how many entries, how many individual data points fell into sort of a category, but in bar charts is when we're talking about categorical data. Bar charts are when we have categories of things such as maybe this is like billions of dollars of goods imported to the US from each of these given countries out here. We could say that China had $90 billion of goods. The US, okay, we're not importing Corcel, had $53 billion worth of goods, whatever. And the important thing here is that bar charts have gaps between these things because there is no measurable distance between China and the US, between the US and France, we don't think that there is any ordering here or any measurement between each of these categories, right? So all these categories are completely distinct from each other, and there isn't some way that we measure them. So there's no numbers on the x-axis here. There's only how many of the thing that we're measuring are associated with that one category. On the other hand, a histogram that you're seeing on the right over here looks a lot like a bar chart, but the difference is that we do have numbers down here on the x-axis. So now this is like saying things like, maybe this is like how many minutes did you have to wait at the airport for your delayed flight? If your flight was delayed, by how many minutes was it delayed? Maybe we're surveying people at the airport. This right here is going to say 30 people had their flight delayed between 10 and 20 minutes. 50 people had their flight delayed between 20 and 30 minutes. 80 people had a flight delay of 30 to 40 minutes. One of the tiny technicalities we might have to talk about here with our histogram is, does the actual value of 20 minutes of flight delay fall into this category or this category? Honestly, that's just one of those things that, like, if you're having Excel make a histogram for you, it's got defaults set in there for various reasons. Those do vary from grouping to grouping. So what's not so important is knowing what the right thing to do is. What is important is that you are consistent and pick something and are consistent with it right there, so that you know, like, oh, this is really 10 through 19 and 20 is the beginning and in the next category, and this is 20 through 29, 30 through 39, stuff like that. I think that's a typical way to do it here. But again, consistency matters more than right or wrong on that one right there. So again, bar chart versus histogram. Bar chart is measuring the number of occurrences or the of categorical data, how many data entries fall into a category. So this is for categorical data. Histograms are for numerical data. So these are for two different data types. And because this is numerical data, because I could say things, and again, coming back to why we don't have gaps here, it's because if you're delayed 15 minutes on your flight versus 25 minutes on your flight, I can measure that difference. I know exactly how much that difference is. I know that 10 minutes or 15 minutes of delay is less than 25 and it's less than 35, right? But it's more than 5 minutes worth of delay, stuff like that. So there is a natural ordering. I can measure distance between the ideas that are on my x-axis down here. And so that is the reason why those bars are all packed up against each other. In the lecture yesterday, you guys saw me, I had a little bit of code and I was like rolling the dice and it was producing histograms because it was counting how many of the dice came up with that roll. So there were 6 columns for the 6 different die outcomes, and the height of each of the bars was the number of rolls that were associated with that one given height. So distinguishing between the bar chart and the histogram is important. When you make bar charts this semester, they better have gaps between them. When you make histograms this semester, they should be stacked up next to each other like this. I do want to, maybe I'll just draw, I'm just going to draw like the tiniest little histogram in here. It's also the case that like, I don't know, it's not like you need to make sure that there's no gaps in your histograms. But we should understand that when we're measuring numerical things on the x-axis that we should have a measurable distance between them. And so it is the case that I will do things like, that's what's going on there. So like I've definitely made like, by hand histograms before where like literally I'm rolling dice and I'm saying, okay, there's 1, 2, 3 dice rolls maybe, and I'm getting rolls of 1, 2, 3, 4, 5, 6 out here. Where maybe I just see like little X's in the box, right? Maybe it's like, oh, I rolled a 1, and now I rolled a 3, and then I rolled a 2, and then I rolled another 3, and then I rolled a 5, and then I rolled another 3. Maybe this is just like my by hand histogram of me having rolled a die 6 times right there. I think just putting like little X's in where you got stuff is totally fine. Other things that I've done in making that exact same histogram is just giving myself little boxes. There's my roll for a 1. Oh, I got a 3. I got a 4, so that one should be attached to it. I got another 3, so let's put another little piece of box on it. Oh, I got another 3, another piece of box on it, stuff like that. So when making these histograms, it's not, I'm not going to like fight you over having these gaps. In bar charts, you should have gaps. In histograms, we're going to make, this is by far going to be our most common graphical display this semester. Lots of histogram discussion, lots of histogram diagrams in the book. And it's, all of these I easily understand to be histograms, as long as we have things like good labels on the X and Y axis and some titles and stuff like that, then these will be lots of options for how you might be drawing your histograms out there. Last thing I want to talk about before we walk away from our graphical displays here is the line graph. We'll talk about this. This will come up a little bit more in the later part of the semester. And here's basically, this is sort of like pie chart where I more have things to say to you when to not do it than when to do it. The important thing about the line graph is that we're going to see later this semester, we're going to see some scenarios in which we're collecting more than one data point for an individual. For example, we might ask a bunch of people, what is your height and what is your weight? And that's going to give me a data point for some people, right? And everybody's going to be a little different. Everybody's a little, differently shaped out there. So we might get a bunch of different points. The important thing in this case is it is never appropriate. It is never appropriate to draw lines connecting data points unless time is being measured on the x-axis. If we're talking about barrels of oil per year for every year, then it might make sense, right? So I'm going to say here, if we're talking like barrels of oil per year that we use as a country, then when we have time over here, that it makes sense for me to draw lines connecting these guys. If this is not time, then there is no lines, right? So line graphs are graphs where lines connect data points. Data points should never be connected unless there is a time-based measurement that is relating them. So line graphs are always associated with change in time. And so that's just to say, don't connect data points unless time is on your x-axis right there. That's all I want to really say about line graphs. We're really going to deal minimally with line graphs. We will see a bunch of scatter plots. This will be like our last unit of the semester. We're going to talk about regression and scatter plots here. So this will be like week 14, week 15. We'll kind of come back and I'll shake my fist at all of you one more time and say, don't connect the dots if time is not on your x-axis. Okay, I think that's it for our graphical displays here. Our next topic here, our kind of like last little things to look at here is sampling, and then I'll talk about variability for like a couple of minutes, and then we'll wrap it up. So, sampling, the goal of inferential statistics, which is a majority of this semester, the topics of inferential statistics, is to infer a truth about a population by only looking at a subset of that population. So we're looking to make statements like, we believe that the average height of all adult males in the United States is 5'10". And we believe that because we took a sample of the population and we believe that that sample was representative of the population and large enough to draw the conclusion that we've drawn, right? So an inference is taking data, a small piece of data, and trying to apply the conclusions from the small group to the broader group. So inferential statistics take a little bit of information and try and draw broad conclusions. When we gather information, the act of sampling or data collection, we want our sample to be truly representative of the broader population that we want to make inferences about. So what matters when we perform any data collection task is that we collect data that will actually end up being a good representation of the entire population. If we take very small samples, then it's easy for us to have non-representative samples. If we only take samples from small subsets of the population, it might not be fully representative of the entire picture out there. So let's say a couple statements about sampling and then look at some good and bad techniques to state the pros and cons. So two broad statements I want to make about data collection before we talk about the data collection techniques that you guys already read about. One, collecting large amounts of good data is very hard. And when I say very hard, what I mean is most of the things that we want to know about in the world, we literally can't afford to collect enough data on. It's just too difficult. There's lots of roadblocks to collecting valuable data. Some of the things that you guys should be thinking about is like, what are like humanity's like big things that we're up against right now? Some of the hardest things that we're up against right now are things like global warming is a thing. Well, what do you need to do to understand global warming really well? We need to collect unbelievable amounts of weather data so that we can actually understand how the weather is changing. Well, that means that you got to do things like put satellites in orbit. Well, that's hundreds of millions of dollars right there. I have, for example, I have a good friend of mine from grad school. He works for a company that does government contracts, and so they do things like military research, basically. And he is currently working on a weather research project where they are attaching little mini weather stations to drones that are all autonomous. Like there's not like a human flying the drone. All the drones talk to each other and they see where there is higher variability in temperature, and the drones will all go focus on that spot because where the weather is changing a lot, then we need more sensors in that area. But where weather is changing over only a little bit over large areas, we can have fewer sensors in those areas. So he's working on a machine learning project, which is essentially teaching all of the drones how to know to fly to the areas where it's most important that they collect the data. So all I'm trying to say to you is like there are like hundreds of billions of dollars that are spent every year on trying to collect good data because collecting good data is hard. Other things out there, by the way, other things that like humanity wants to try and do is like cure cancer. Well, guess what? It's really hard for us to study brain cancer because it's really difficult for us to. First of all, not many people get brain cancer, and the ones that do aren't really interested in just saying like, yeah, go ahead and cut my brain open and go ahead and do all the research that you need in there. It's really hard to get our hands on good data for some really important things, right? So collecting large amounts of good data is very hard. And I actually want to say one other thing about this real quick. Let me do this real quick. Let's just Google something real quick here. I want to Google something. Cost of The U.S. Census. $15.6 billion, right? So every 10 years, the United States performs a census. It's allegedly happening in 2020, despite some best efforts out there. But this is an insane amount of money. This is a huge amount of money, but that's because it's so valuable for the United States to know who is living here and what demographics they fall under. So that, well, the purpose of the census is supposed to be to help us be better represented in government. It's Okay, never mind. I'm not going to go ahead and talk about that right now. In any event, it used to be very valuable to us as a country to know the people that were in here so that we can help them. And that this cost right here, this price tag, is representative of how valuable this information is to us, right? So collecting valuable data is the big thing right there, right? The second thing to say here is that there is not a single best method of sampling. There is not some like gold standard where it's like, oh, you did your sampling technique that way, then this is good. There is no one sampling technique that is best for all scenarios. There just isn't. What context you're in will determine what is best in your scenario. And even at that point, this is very regularly a thing in lots of statistical articles and journals, stuff like that is saying, there's just debate. Like, was that really the most appropriate way for you to collect that data right there? It's always a point of discussion in any statistical thing that happens is, was that the most appropriate way to collect data? So there is no single best way to collect data. So we want to look and see what are the pros and cons of all the different types that are out there. So there are some good sampling methods, and I put good very much in quotations there on purpose because even though these are good, they can be used incorrectly to result in very bad samples. So these aren't just good all around. These are some smart things to do that might help us out, right? So simple random sample is always the basic thing that's kind of laid out as the first type of thing. This is super common enough that it gets its own abbreviation when pretty much nothing else ever does. Simple random sample is common enough. I used to think that this phrase was dumb because I'm like, why do we need simple? Can't we just call this a random sample? Because nothing else is just called a random sample. But I have come to realize that I do like the word simple on it because it's indicating to me that nothing special was done. It's simple. There can't be any rules if it's a simple random sample. It just has to be random, and that's it. So this is saying each person in the population is equally likely to be selected. It turns out that simple random samples are, in most cases, the best thing that you can do, making everything equally likely. But it also turns out that there are lots of scenarios in which you will miss the most important data if you take a simple random sample, and so it is definitely not the best thing to do in all cases. The immediate counterexample is the second one, stratified random sample. A stratified random sample is where we place everybody into certain groups, and then we take a sample of the same number of people from each group. So here's my example for stratified random sample of when I think it would be better than a simple random sample. Suppose that College of the Redwoods was trying to collect information on how they should proceed with forming a new multicultural center. If the college took a simple random sample of all of its students, then what it's going to get is a representation of the student body at College of the Redwoods, which is going to be over 50% white. I don't necessarily think that all of the Caucasian students at College of the Redwoods are the people that need to be consulted about a multicultural center. Now, that's not to say that their opinion doesn't matter, but I think that in this case, what I think would be a mistake would be to try and collect information on what people think we should do with a multicultural center and collect data only from a majority of a majority ethnicity rather than the minority ethnicities that their multicultural center presumably would be most focusing on advocating for. So in the case of this scenario where we want to collect data to improve the multicultural center, I think it would be much better to do a stratified random sample. In this case, we might say, let's categorize all students at College of the Redwoods into maybe like the 5 largest ethnicity groups. Maybe this is Caucasian, Latin American, African American, Asian American, and maybe like an other, or sorry if I'm forgetting any major groupings out there, but that's not the point. The point is we could place all these groupings and then say, let's randomly choose maybe 50 students from each of these groups out there. What that does is it prevents the fact that there is a majority of Caucasian students at College of the Redwoods. It prevents that majority from being the majority voice heard in the sample right there. And that's really important. If what we're looking for is to get information from historically underrepresented students, then what we want to do is we want to actively make sure that they do get the representation, and that happens in the stratified random samples. So in the case where it's very important that you hear from minority groups as much as majority groups, stratified random samples are good ways to make sure that you hear equally from different categories of groups. Other things that happen with this is like in school settings, a stratified random sample might be like, let's sample 5 faculty from each division and see what they're doing with their online classes. Since it might be too much for the school to like kind of investigate what all 100 faculty are doing at CR, maybe they just randomly select 5 people from each division, because that'll give them a snapshot of what's happening in each division. It helps make sure that even if there are smaller divisions, that they are still looked at just as carefully as the larger divisions, stuff like that. So it helps kind of in a sense promote equity across groups where there is not current equity. So it brings equity into the sample where there is not equity in the population, maybe is a good way to think about that. Cluster sampling and systematic sampling are typically done to help make things a bit easier for the sampler rather than to help increase the goodness of the sample that is taken. Cluster samples and systematic samples are both just ways in which you choose which people are going to be part of the random sample. So in a simple random sample, you should think of that as nothing more than just drawing names out of a hat. In cluster sampling and systematic sampling, there is sort of one step that is like drawing a name out of a hat, but we do much less of it. In a simple random sample, if you're going to draw a sample of 50 things, then you're pulling 50 names out of a hat, and those are going to be the 50 people that you're sampling, or 50 entities that you're sampling. In a cluster sample, we might do things like, I think the book's example is like putting students in, randomly selecting a row and a column of students seated at tables, and then only checking the homework of the people in the given row and the given column. So notice in that case, even though there's 30 students in the classroom, and even though you're planning on sampling maybe 15 of them, there's really only 2 draws of the hat. One draw for a row number, one draw for a column number. So it's really saying, let's put everybody into groups and only grab the information from a couple groups. This is different from stratified random sampling. In stratified, we put everybody into groups and we take an equal number from each group. In cluster sampling, we break everybody into groups and we check everybody in only a couple of the groups. In a systematic sample, this is another similar thing where we just kind of reduce the amount of overall random draws from the hat that are being done. In a systematic sample, we're going to say something like, we need to go survey all the people in this neighborhood here. So let's randomly choose a starting house. That's the draw of the hat. Out of the 100 houses in the neighborhood, we're going to sample 30 of them. Let's randomly draw one house, and then let's visit maybe every 4th house after that one right there. So in that case, there's only one random selection that was made, the starting house. And then the systemic part of it, the systematic part of this, is that we systematically then proceed to every 4th house maybe afterwards. So there's sort of an initialized random part to it, but then it is systematic after that. But the point is that should probably, in most cases, end up giving you something equivalent to a simple random sample, unless you're in a neighborhood where it's like every 4th house is a corner house. And maybe corner houses are less valuable because people don't want to be living on intersections where there's cars. And so those all have lower home values. So the systemic samples can bring up problems where if it accidentally ends up being the case that every 4th house has some special property, then you just totally missed getting a representative sample. So systematic samples are good because they, in a sense, reduce the effort required by the sampler. But you really got to be careful that you didn't accidentally pick one sliver of the population out by doing your systematic sample. So all of these are considered good sampling methods. They all have pros and cons. They all have like risks associated with them that you might not capture the information that you're looking to capture. And so while all of these are under the umbrella of good, these can all be misused in ways that make them bad. And so that's why we get good in quotes there. Very similarly, these are considered bad sampling methods, but there's just no way around using them sometimes. Absolutely, convenient samples and self selection samples happen all the time because, as I said, good data is just hard to get. If you're a researcher, you got to do whatever you can to try and get good data and try and understand is that data useful or not, right? So, in a convenient sample, this is when we're grabbing objects that are convenient to the sampler. All right, so this is like going to the mall and surveying people. I'm pretty sure everybody has been annoyed by ever being asked to take a survey by a person standing at the mall, but it's their job. But that's just out of convenience because the mall is an easy place to get at people. All right, calling people on the phone is typically considered a convenient sample because calling on the phone is a convenient way to get a hold of everybody. But not everybody. I just misspoke there. Some people don't have a phone. Some people don't have a listed phone number. Sometimes there's households that have 10 people, but there's only one phone. So did you really get everybody if you just talk to somebody on a phone? So things like that, convenient samples, they are going to end up only getting information from the people who are convenient to access. And that's definitely not always going to be everybody. Self-selection samples are also very bad. I always feel very obligated to mention these when I teach this course specifically because self-selection samples have become wildly more prevalent with the advent of the internet. A self-selection sample, I think that the most classic ever self-selection sample is something like, do you think that Donald Trump is a great president? Yes, no, maybe. The only people that are going to respond to that poll are the 5% of people that love Donald Trump the most and the 5% of people that hate Donald Trump the most. People that feel neutral towards a topic are never going to choose to participate in a study about that topic. And I shouldn't say never, that's a bit of an exaggeration, but self-selection samples where the individual get to choose if they are part of the study or not almost always biases itself towards the extremes on both ends. It's the people that feel strongly one way or the other that are more likely to choose to participate in the study. And so self-selection samples are almost always biased towards the two extremes because people that feel neutrally about a topic aren't going to go out of their way to participate in it. I'm not going to click on an ad that says, I am neutral about so-and-so candidate. It's only the people that feel strongly that go out of their way to participate there. So self-selection samples often end up biasing towards the extremes rather than getting a full representation of all the people that might feel neutral. The last thing that I want to say here is, and it's really important, this isn't a sampling method, and I put this here because I think that there's some like homework questions and some textbook questions that include like sampling bias as like a sampling method. This isn't a sampling method, but I want to share with you like a thing that happens also in some other sampling scenarios. So another way that that bias can creep into our samples here, where bias is our sample taken leans towards something unfairly, right? And that's bias in a sample. One of the ways that bias can creep into a sample is if the person collecting the data has an expectation of what overall data they're going to end up seeing. And so here's the experiment that was done with this. So this is one of those experiments that was done where the people didn't know that they were part of an experiment, right? So these researchers took groups of people, and what they wanted them to do was it was something like go ask for like political donations or go ask, this might as well be like, will you buy my, Girl Scout cookies kind of thing right there. So this is going door to door in a neighborhood. And what they said was, we want you to go door to door and ask if they'll, support this political candidate or give us this money or whatever. And what they did is they broke all the people that were doing the door to door, and they broke them up into two groups. They sent them both to what they had previously determined to be very comparable neighborhoods in terms of all their political and financial and education demographics. And they said, you guys are going to go to neighborhood A, you guys are going to go to neighborhood B. All the people that were going to neighborhood A, they took and they said, listen, you're going to go and ask these people for this political donation. Based on what we saw last year, we expect you guys to have about a 60% success rate. We think about 60% of all doors that you knock on, the person's going to donate to you. Then they took all the people that were going to neighborhood B and they said, listen, you're going to ask all these people for these political donations. Based on last year's numbers, we expect you to get about 20% success rate. We expect about 20% of all the doors you knock on, people are going to respond positively and give you the political donation, right? So what ended up happening is they sent these groups out. One was told to expect 60% success. One was told to expect 20% success, even though the neighborhoods were essentially equivalent to each other. And what ended up happening is Group A came back with about a 60% success rate, and Group B came back with about a 20% success rate. So because the people that were actually involved in actually doing the experiment had a preconceived notion of what they thought their success rate was going to be for all the yes and no's that they interacted with, that actually ended up influencing the outcomes that they end up seeing out there. I would have to imagine that the people that were told to expect a 60% success rate are thinking in their heads, I am anticipating more than half of all people are going to be into this. So therefore, when they give their little pitch, I think they have a little bit more confidence in their voice. They think that they're going to be successful, and so they were. The 20% people are like, listen, most people aren't going to be in this. This is only like 1 in 5. So I get it that people aren't going to want to be into this. I probably won't badger people too much when I go to do this. And then they ended up with a 20% success rate. So even just thinking that you know what outcome you're going to get before the experiment starts can ruin the experiment for you. Your preconceived biases about what outcome to expect can influence the outcomes that you get. So that's why it matters that we do things like set up like double-blind experiments where people don't even know what treatment group they're part of, because that helps prevent that preconceived bias from creeping in right there. So again, that's not like a sampling method, but other sampling bias can creep in, especially related to expectation of certain types of outcomes. And so avoiding that's really important if what we're trying to do is get a good snapshot of the true population out there. So last thing, just 5 more minutes here. Let me just say our variability statements. If we'd like to make confident inferences using data, then we need to use a representative, non-biased sampling method, and we need to collect a large sample. We're going to spend kind of a lot of time this semester talking about what large means, and it's different in every context, which is a little bit annoying out there. And the answer is it's going to change all the time, right? So if we want to make good inferences, then we want to make sure that the data that we collected is truly representative of the population. That'll happen if we use a good non-biased sampling method, and it'll happen if we collect a lot of data. But the question is, how large does the sample need to be? Well, it depends on the amount of variability in the sample. And here, let me say this is just my last thing for the day here. Think of this example. Suppose that we want to make an estimate for the average height of all adult males in the United States, and we want to make an estimate for the average weight of all adult males in the United States. I think that we require a different number of sample to be taken for each of these because of the fact that there is different amounts of variability in each of these data, right? In each of these variables. And what I mean by that is height for adult males does not vary a ton. And if you think about by like what percentage taller or shorter you are than other people, most people, it's a very small value. On the other hand, weight varies significantly more from one person to the next. And maybe here's my like simple statement to describe this. I do know more than one person that is twice as heavy as I am, and I do know more than one person that is half as heavy as I am that are adults. Okay, I guess those are females that are lighter than me. But still, like double and half, that's extreme. There's lots of variability in weights. On the other hand, I absolutely have never met anybody that is half or twice as tall as I am, right? That doesn't happen. So height variability is much lower from person to person, and so therefore we won't need to take as many sample points to get a good picture of what average height is going to be. Weight varies significantly more from person to person. The amount of variability in that variable, person's weight, is much higher than it is for height. Therefore, we're going to need to sample a much larger group out of the population so that we make sure that we've gotten a more representative sample since the amount of variability is much higher. So a thing that we are going to want to measure this semester with using things like interquartile distances and standard deviations is the amount of variation that we see in a data set. The more variation there is, then the larger the sample we're going to need to be able to draw good conclusions about that variable. And so just stopping and thinking like, how much does this variable normally change, right? Because again, a person being 300 pounds is really not that unusual. A person being 110 pounds is really not that unusual. But a person being 7'6", that's really unusual. A person being 4 feet tall, that's really unusual, right? So we want to stop and think like, how much variability would you consider a normal amount of variability? If it's large, we need more data points to get good pictures of the whole population, right? So again, the book is constantly bringing up variability, and it's constantly not really defining it yet. It just wants us to keep saying, remember that every sample that's drawn is going to be different, even if you use the exact same techniques. And remember that all variables have different amounts of variation that we should expect when we draw individuals from a sample. Some things are very, very, very consistent. Other things have a huge number of possibilities that could occur. And how much variation there is will inform us how large a sample needs to be for us to be able to draw smart conclusions. And that'll all be thoroughly discussed at length in multiple sections this semester. So that's my last things for 1.2 right there. I went a little bit long, by the way. I do just want to say, like these lectures, in my mind, they're all going to be an hour, but they're probably all going to be more like an hour and 15 minutes here. I do think this is about a typical to be expected time length, particularly when we actually get into our more computational and more technical writing later this semester. We're going to need the time. So I do think this is a reasonable time length right here. So that's it for this week. So this is my second video for this week. This week we're really just looking at sections 1.1 and 1.2. My last thing I want to say, I guess, is this week had the least content of any week of the whole semester by a lot, by like a lot. And that's because I'm assuming that all of us are kind of still working through figuring out where things are in Canvas. Getting all of our information, getting set up with MyOpenMath, doing your intro quiz in Canvas, doing your intro PDF assignment in Canvas. There's obviously just a bit of administrative things that we're all also handling this week, getting on board with our online class here. So just be aware, this is, in one sense, very little content for this week, but I also know that you guys do have other things that are being handled. So just expect that next week and in future typical weeks, it will be much more common for me to be covering multiple sections in a day and for those sections to have more content in them. So it really does matter that you keep doing things like doing the reading and the comprehension quiz before watching the videos, because as we get into the more complicated content this semester, I will be leaving off the basics in my video like I did with lots of definitions today. I expect for every video that you've always done all of the reading and the comprehension quiz before watching the videos. That will allow me to keep the videos as short as possible, so I'm not filling in all the basics. I'm really just doing more of the high level stuff in the videos. So yeah, so this is it for our videos for this week. Next week we're doing 1.3 and 1.4 and 2.1 and 2.2. So those will be 2 sections on Monday, 2 sections on Tuesday for our 10:30 videos here. If you guys have any questions, as always, hit me up in the email. You guys should have both your intro to MyOpenMath homework as well as a week 1 homework. So there's 2 MyOpenMath homework assignments that should be open right now. The intro assignment is due this Saturday. The week 1 homework is due at the end of week 2, as will always be the case this semester. There's always 2 weeks of open time for those homework assignments there. So there's also your intro quiz and your week 1 quiz as well. So you do have a handful of things to do, but they're all relatively small things. So keep looking through Canvas for all of your total things. There should be your 3 pre-assignments and your 2 week 1 assignments, Canvas quiz and MyOpenMath homework there. So 5 total tasks that you should be looking at to hopefully be completing this week. Okay, actual last thing here. MyOpenMath homework is open until next Saturday, so you always do have 2 weeks to do the MyOpenMath homework. That's really just to make sure that everybody has enough time. Your goal for the semester should certainly be to always do the homework within the week that it's in, so that the next week you can just move on to the next week. Don't fall against the back half of our schedule. You should try and keep up with this stuff. Just knock this stuff out and do it. It makes it so that if you get stuck and need help, you have plenty of time to get help without that affecting anything as far as the deadline goes. So even though those deadlines are all a week deferred for all of our homework all semester, try and get all this done in the current week. It helps. Everything will be better for everybody when you do that. And I think that you know that is the case as well. So try and stay up with that stuff. Let me know if you guys have any questions. Otherwise, I'll see you at either office hours later this week or at our lectures on Monday and Tuesday next week. See you guys then.